I'd like to start with a general overview in regards to the metrics of the passive house. The passive house concept is not in opposition, but the passive house concept is a performance-based concept. We look at the performance of the house first, and this is what you just got in terms of your on the sheet with the metrics of the passive house. So a lot of people always ask me, where do these metrics for the passive house come from? And is it an arbitrary metric, or how does it relate to the situation that we find ourselves in today? And this is what I would like to start with. I would like to start with the 2000 Watt Society, which came out of the Nova Atlantis Institute in Zurich. And the 2000 Watt Society is a concept that was based on looking at how much energy can we actually afford to use per person. So they're saying we need to start in a sustainable energy economy. And if we look at the slide right here, we can see that the per person energy usage worldwide is in great inequality. In the United States, we're using currently 12,000 watts per person continuous energy usage. In Europe, they're using about 5,000 to 6,000. In Bangladesh, it's only 200. So if we really truly want to create a sustainable energy economy, how much is that per person if we look at the overall global population? And we come out to 2,000 watts per person. Why is this important? Of course, there's another factor, the peak oil factor. Some people say we are already past peak oil. And from now on, the oil price will only go up. Right now, we're seeing the oil prices drop temporarily. I believe that in about 2 years, it's going to go up to pretty unseen heights in terms of oil price. So we have these fossil fuel sources available to us to cover our energy needs. But if we then look at the International Energy Agency's World Energy Usage Outlook, we can see that they are proposing an increase of about 60% worldwide. So with India and China coming onto the market and also wanting a piece of the pie, our energy consumption is projected to go up by 60%. If we do business as usual in terms of like we rely on fossil fuels to provide our energy, this is how it's going to look like. But this is, of course, as we saw previously with peak oil, this is not going to happen. We will not have enough oil available to us. So with the 60% increase in energy consumption, we get to the next problem. We are already using so much fossil fuel right at the moment in terms of CO2. Global warming has reached a very critical level. And I don't think we have to debate necessarily anymore if it is true or not. Even if it was not true, I really would not want to take a chance on that one. We already are emitting so much CO2 that we theoretically would need about 2 atmospheres to safely handle that CO2. So we are already in a very critical zone. So now we're looking at the next, 20 years, we're looking at an increase in world energy consumption of about 60%. So we are in real trouble if we are intending to provide that energy through fossil fuels. So what are our options? Our options are these percentages up here. We have nuclear available to us. We have renewables available to us. We have biofuels. And we have efficient technologies. So now there's a myth out there that we have enough renewables on this planet to cover all our energy needs. I don't know who of you has heard of the Plan C book by Pat Murphy. This just came out this past August. He goes through the numbers in terms of like how much energy we're using worldwide, and how much renewable energy is actually available to us. It's not that we don't have enough available. The limit on that end is actually a financial, economical limit. Like if we look at like how much energy we need to provide with windmills, let's say we are trying to provide all our energy through windmills, this would come out to about 13 trillion windmills. So once you look at like how much does a windmill cost, and even without maintenance, at that point we very quickly see that the limit is the economy, the money that is available to buy these renewable sources. So limited. Okay, so with the passive house technology, we have the chance, if we start building now, every single new construction, newly constructed building, and we start retrofitting at the same time, we actually have a chance to bring the worldwide energy consumption down in terms of CO2 emissions as well. So then by 2030, we're expecting another push in terms of renewables and in terms of energy efficient technologies. So with the passive house technology, we can almost stabilize the climate. And why passive house and the building sector? Because about 48% of CO2 emissions are caused by the operation of our buildings.
But this is worldwide, right?
This is worldwide, yeah. Okay, so this is kind of like the big picture. Why passive house? It's a very crucial factor that we reduce the CO2 emissions through the operation of our buildings. And how do we get there now? What does that in essence mean for how we construct our buildings? So now we kind of like turn the concept around. We have built our houses so far the same, like south, north, east, west, 2-by construction, and then we put a variable, usually oversized furnace into the building to condition the building. So now the passive house does the opposite. It says like, okay, we look at the big picture, and by looking at the big picture of the sustainable energy society, we have to reduce each person's consumption down to 2,000 watts. How much is that? How much can every person then afford to heat their houses with? So when we have the little picture of the hairdryer right there, for a passive house it comes out to about the energy amount of a hairdryer. So yeah, that might sound too good to be true. But it is a very stringent energy standard, but it is actually possible. And the reason why it's possible, and again, the same principles as we have been using in the early 70s for the passive solar houses. We use passive solar gains, orientation, we use internal gains. So again, the main principle is minimize all the losses first and maximize the gains. Build the shell. The shell becomes the variable, no longer the heating system that we put into the building. So this is a very important concept, and it took me a very long time to actually realize that we're taking the same amount of energy if we're in Minnesota, or if we're in Miami, or if we're in Berkeley, or if we're in New York. All houses are going to be heated by the same amount of energy. And then the shell is variable and changes depending on climate. So why positive net energy home? A while ago, I started looking into the definitions of the zero energy home. And then once you look into that, you very quickly get to like, okay, the definition of the net zero site energy home. Then you get to the net source energy home. And then you get net source. And then there's a school of thought that says, well, that is all not good enough yet. We really have to go to net zero emissions. And what that means is we have to overproduce to actually offset the carbon that we have generated through building our building. And this is what we're seeing right here. The passive house concept reduces the overall energy consumption by 90% for operational energy. And that means that the overall total household plus operational energy is reduced by about like 70 to 80%. And at that point, if everybody did that, we're getting into the realm where we can provide our remaining energy needs through renewable sources. we have about 20% feasibly available to us. So this is a slide. This is from the McKinsey quarterly report, and the International Energy Agency at the Passive House conference in Germany this past April. They had a presentation, and they were pointing out the cost for carbon sequestration. And I'm not planning on going into great detail with this slide, but the interesting part right here is the building insulation. The building insulation is the biggest bang for the buck. This is our cheapest way to reduce our carbon emissions. And this is really good news. And also, insulation is the cheapest material in construction. So we will see that this is actually cost effective to do. This is the kind of like the interior economic feasibility of the passive house concept. Dr. Feist and Bo Adamson, they went ahead, they established the passive house concept, and they defined the metrics of the 10% of the factor 10 energy reduction and overall 70 to 80%. And they looked at what happened in the 70s in the United States. So a lot of people always tell me, well, passive house is really a European concept and it won't work in the United States. Well, as you all probably know, the Small Homes Council here in Illinois, Wayne Schick, has the honor to have coined the term super insulation. So the super insulated house is really, Urbana is the birthplace of the super insulated house. And they looked, Bo Adamson and Dr. Feist, they studied all these phenomenal projects. Harold Orr, the Saskatchewan house, I had the pleasure to meet him personally last year. He's a phenomenal person. He's still out there building and retrofitting houses to passive house standard right at the moment. And then, of course, Amory and Hunter Lovins, tunneling through the cost barrier. Amory Lovins built his Rocky Mountain Institute in 1984. It was on the cover page of the Solar Age, I believe. That was the magazine. That was in 1984, and then 1985, 1986, there was a change in government. Energy became cheap. That magazine that was at the height at that point completely vanished, and all the super insulation knowledge basically got lost. And it's really amazing. I recently I bought the book by William Shercliffe, The Super Insulated Houses and Double Envelope Houses. If you look at the details in this book, we had it all there. We had it all in 1978, 1980. We had it all. So now we're kind of like coming back full circle. In Europe, they felt the energy crunch much earlier than we did over here. So they started investing into energy conservation. And they recovered all these ideas. They recovered all these details. And that is finally the result of what all these architects and scientists came up with. This looks kind of abstract at first, but this is the economic feasibility curve from the inside. Of course, if we tell people they need to super insulate their buildings and they need to use like super insulated windows, and it's completely unfeasible for people to do, nobody is going to do it if it is too costly. So what they found in 1996, when Dr. Feist built his first passive house, they found that until then it was believed that 40 kilowatt hours per square meter in a year, a low energy house, was the most cost effective that you can do with super insulation and conservation. So that is, for a little while, that is the case. The additional upfront cost to make your house more efficient seems to increase exponentially, as you can see right here. But then at a certain point, the further you push it, at this point, something very interesting happens. Your energy consumption gets so low that you can basically heat your house with 10 candles, back to the hairdryer, right? So at that point, you can eliminate the traditional furnace. The furnace goes. And at that point, you get an incredible cost advantage. And that's really where the passive house concept started to make incredible sense. So that was the beginning of understanding, okay, if we reduce our loads to that point, we have a cost advantage and we can actually make it work from an economically feasibility point of view for the homeowner. So, and of course that was just the beginning. They realized that this drop was a good point for the metrics to define. And that metric is the 90% energy. Oops, now that's weird. Back to that one. So to build a passive house, though, this is not where it stops. It's not good enough to just super insulate and then eliminate the furnace. It takes integrated design principles from beginning to end. We cannot just take a design and then put passive house on it. What is really critical to make it possible and economically feasible is to build it into the design right from the beginning and to uncover every single cost trade-off that we can find. And really good integrated systems designers, they can build passive houses today for the same cost as it costs to build a traditional building. So why wouldn't anybody do that, right? If that was the case, and it is the case. I've seen two people in New York, which I respect greatly. They are the masters of cost trade-offs. They managed to build passive houses today for the exact same cost as a traditionally built building. What they do when they get a job, they get the first baseline bid and then they work towards it until they beat it. So the baseline bid is the International Energy Conservation Code 2006, and the passive house saves 90% in operational energy compared to that baseline bid for the exact same price. So how do we get there? What are the main design principles, envelope and thermal comfort principles of the passive house? Number one, we talked about this super insulation, continuous insulation. This has a very nice side effect, which is it creates very steady indoor temperatures. Also for second homes, very nice. Temperatures never drop much more below than below 50 degrees Fahrenheit. So no more pipes are freezing. Then thermal bridge-free construction, very, very important. As soon as you insulate your envelope to a level where you cannot have any heat loss, like every single thermal bridge, small thermal bridge, a connection into the structure, like any kind of like fastener that goes through any kind of window frame that is not thermally broken, becomes very pronounced. So we need to make great effort to design the entire building shell without any thermal bridges. Compact building shape, that is the most energy efficient shape to start with if you design a passive house. The Europeans love it. They love their boxes. They love the modern design. A lot of people don't go for it. It's not a problem. I have an example later, which, like, the architect basically did everything wrong that he could have done wrong just to start out with. And we did achieve passive house standard. So it is not impossible to take a shape that is a little bit more complex. Passive houses do not have to be boxes. Airtightness is probably the most challenging aspect of a passive house. It has to be super, super, super airtight. The airtightness is about we require 0.6 air changes per hour at 50 Pascal. So that is very, very tight. This is virtually airtight. Very difficult to achieve. It takes very careful planning in terms of the airtight layer. It challenges the architect. There's a new sheet that needs to be introduced into the design set, drawing set. We have to have details how we connect our airtight layers in the various components to each other. Otherwise, on site, it will never happen. You will never get there. Balanced ventilation with heat recovery and minimal space conditioning system. This is the wonderful core piece, the heart of the passive house. What this curve, remember the curve? Like we were pushing, making the envelope more energy efficient, and then all of a sudden it drops. So at that point, the traditional furnace goes, But at that point also the house is very airtight, so we need to bring in fresh air. We're starting to introduce the balanced ventilation system. That has also a nice side effect. The indoor air quality in passive houses is outstanding. In Germany, at first, people said, like, I don't want to live in a thermos bottle. They were very suspicious. And then they did some testing. And because the ventilation system is running constantly, it's constantly bringing in fresh air, exhausting all kinds of the moisture and the pollutants to the outside, they found that actually the indoor air quality of a passive house is so superior that they started recommending passive houses to people with allergy problems, health problems, chemical sensitivity problems. So now remember the hairdryer. We still have to introduce this tiny little bit of energy. We are not completely heat free. So this is another little trick of the passive house principle. You're introducing this last little bit of heat or cooling into the minimized duct of the ventilation system. So at that point, the duct system is minimized, very small, and it's basically a low flow furnace. The fan of the ventilation system becomes our air handler. And the heat source is introduced into the ventilation system after the air goes through the heat recovery. Optimal solar orientation and shading, that's natural, yes. If we have free solar gains available to us, we should orient the building accordingly. Of course, that is not always possible. There are lots in the city where we have absolutely no solar access, lots that are facing north. All that is also possible. It's not an obstacle. Energy efficient appliances and lighting, this is a given. We have to keep our loads as low as possible. Somebody might go ahead and say, like, wow, this is great. I can heat my house with like 10 incandescent light bulbs. Of course, in the summer that will work against you. It's going to be a liability and add to your cooling load. So rule number 1 is don't put lots of electrical appliances into your house to heat your house with. Reduce the load on those appliances first. And then very, very important, the user friendliness. What we do, we design passive houses with a dial 1, 2, 3. That's it. And people have to exchange the filter in the ventilation system every 6 months. And people are used to that, to do that with their furnace anyway. So that's also not an obstacle. This one, I'm not sure why this is not working. So the conventional house, this guy is pretty unhappy, right? So why is he unhappy? Because the interior surface temperatures are very different from the exterior surface temperatures. And that is due to not sufficient insulation. Low surface temperatures equals discomfort. Everybody knows that from large windows, like right here we see it, like all kinds of like heat sources under the full height windows, because the windows are most likely not very high in R value. So what happens is we're getting a convection loop going in front of the windows, and we have to introduce a heat source in front of it so that we don't feel uncomfortable. In a passive house, this no is being transferred into a yes, and a very happy guy. And the reason for that is that the exterior surface temperatures have been brought up to a level that the difference between the interior surface temperatures and the exterior surface temperatures is minimal. So now this guy is very happy. Yeah? So, and that also leads to interesting side effects. When I went to architecture school, I was being told, like, I need to place a heat source in front of the window. Once you start using these super triple pane windows, very high in R value, the convective loop is actually eliminated. There's no need for a heat source in front of that window anymore. For full height windows, no more necessary. This is basically here you can see in a passive house, it's almost even. This would be really cold. In a passive house, the heat distribution is, it does not lead to convective loops that feel uncomfortable. And how do we get there? So now the windows and doors are probably the biggest obstacle that we have in building passive houses in the United States today. And the reason for that is that the window industry has come up to speed with glazings. There are glazings available that are fairly high in R value so far. Still, the spacers might be a big problem because still there are potentially aluminum spacers that are being used in double pane and triple pane windows. Not all windows are using super spacers yet, which have no thermal loss around the edge of the window glazing. But most windows that we see today in buildings have no insulation in the frame. So if we look at the glazing to frame ratio, it's quite amazing. There is a lot of frame around a window. And in most buildings, there's a giant thermal bridge around the glazing, and that is the frame. So in a passive house window, we consider the frame to be a thermal bridge, and we conclude that we have to insulate it. And here are probably the two best windows on the planet. This one is a wooden window that is insulated with cork. So it is not only one of the best performing windows, it's also basically cradle to cradle, which I like a lot. The other window right here is insulated with graphite enhanced high density EPS, which is the best of the foams. I gotta know how many of you have looked into the environmental impacts of foams, polyurethane foams. They are now expanded with non-ozone depleting agents, most of them, but a lot of them are still expanded with agents that have about 1,000 times the global warming potential of CO2. So, and I just recently got hold of a study that basically suggests if we go ahead and spray foam our building, the payback, the amount of CO2 damage that we do right up front by foaming the building, the payback is, I can't even repeat it. My worst fear was like maybe 50 years. Some of the case studies said 300 years. So if everybody went ahead right now and spray foamed their buildings, as far as I'm concerned, we can kiss planet goodbye. So really the idea here is when we go ahead and super insulate and build passive houses, we need to be very clever and very smart so that we don't create unintended side effects. And again, some people say like, well, okay, if I do damage first enough and then I save the energy again, and then that's not, remember the picture with the energy increase? We need to bring it down. We need to get ahead. And that goes back to the positive net energy home. We need to produce more than we consume. And then there are a couple of really fancy systems as well by now in Europe, and it's really exciting. This is a curtain wall system with a U value of 0.8. It is 0.14. And this at that point it gets really exciting. As soon we can build any building to passive house standard with those frames. And then of course doors as well. Doors have to be super insulated. They have to be super sealed. The doors that we've been using so far, they all had like multi-lock systems. Because again, remember, one of the passive house principles is to build super airtight. And if we use a typical door and it locks only in the middle, it starts to bow and we have absolutely no chance to make this door airtight. So now, you might say like, so what am I going to use for my walls? Really, as wall construction, as far as passive house is concerned, everything goes. Everything and anything. As long you meet the thermal resistance requirements for your climate. You can use foam, you can use cellulose, fiberglass, straw, cotton, wool, whatever works in terms of thermal resistance for your climate. And these are the insulation materials that I kind of prefer right at the moment. I try to use only expanded polystyrene for the reasons that I mentioned earlier. Expanded polystyrene is expanded by using pentane, which has only a global warming potential of 7. It is formaldehyde free and it can be recycled. It can be used underground. It can be obtained in high densities, so you can insulate under the footing, and also it increases the R value significantly. Cellulose is the uncontested winner champ of insulation. The embodied energy in cellulose is so low. It's a wonderful material. If this is possible for your climate, we have not been able to use it here for our small homes because the R value did not just make it with cellulose, but cellulose is the absolute best insulation material that I can think of, if applied correctly, of course. There are issues with settling, but if applied at the right density or in dam spray, that can be prevented. We have been using high density spray in fiberglass with great success. It is very cost effective. It doesn't settle. And I have a couple pictures later that show our prefabricated panels. If you start to prefabricate panels for passive houses, you need to concern yourself with the settling. I would have loved to use the cellulose, but we were transporting the panels from like Arcola to Urbana, and it was traveling across the highway. So we were concerned with the settling, and we used fiberglass instead, and there was absolutely no settling whatsoever. They had forgotten a window in one of the panels, so we had to cut into it on site, and it was absolutely solid. There was nothing. Mineral wool is better than fiberglass, and in the next projects that I'm going to do, I'm going to try to get my hands on the mineral wool, much lower in embodied energy. And then I don't have a picture of the vacuum insulation right now. This is the fiberboard right here. Fiberboard as sheathing on the outside gives you a certain R value. The vacuum insulation is a very cool product. It's fairly new. It basically looks like vacuum sealed coffee, just that there's silica in there. And a half an inch has about like 15 to 20 R. So all of a sudden, the thick wall is not an issue anymore. And they're starting to bring the price down. There's also another really cool product, which I just came across in New York, and it's called it's basically the Aerogel. And that company is weaving the Aerogel into a blanket that looks like jeans. And that can be attached to drywall. And that also has per half an inch about like an R20. And the square foot price is about $7 or so. So it'll come down. As soon people start using these products, we will see the prices come down. Again, you can use straw. Here's a picture of Julie's house. You can use straw board. You can use stud construction, double wall construction, ICFs, anything works as long as you meet the thermal resistance. Okay, so now a couple examples that we have been building here in Urbana. This is the first Fairview house, which was basically the prototype. We still built that building on site. Todd was working on that project as well. So that was still very cumbersome. We were really pioneering the system, and this is a construction manual by Truss Joist. Unfortunately not available in English and not available in the United States. I've been talking to them for a while now, and I'm trying to get them interested, to tell them like your product is a prime product to create very thick and well insulated walls. So we have been working with these details, and they have been working very well for us. And this is a picture of the Fairview house under construction with a structural fiberboard sheathing on the outside. And then the insulator goes in on site, nets it, and then fills it with high density fiberglass. So the first project was still very difficult and like piece by piece, and we did not make our goal of beating the cost barrier. We needed to bring the cost down. So we decided to prefab the panels for the next project in the shop. And that was an incredible cost advantage. The house went up basically in a day. And it's amazing. It brought the cost down considerably. And then once it's, I did something. Hit that button again. Huh. I hope it's not stopped. Stop. All right. So the shell then is being built in a day. And the panels are all continuous. When you build by standard construction practices, if you go with platform framing, the penetration of the floor plate to the outside is a huge problem in terms of air tightness. So in our designs, we are designing the entire shell basically super insulated without penetrating through that exterior envelope. This is an interior installation layer, which we also introduced after the experience with the first project. Now the plumber and the electrician, they can go in and they can do business as usual. It also is our bearing wall for the floor plate. At that point, the inspector has absolutely no problem because it's business as usual. So the super insulated panel basically becomes a curtain wall, if you want. And then business as usual, the interior wall also gets insulated. Everything is the same. And these are the two passive houses that we have built. They are on Fairview Avenue in Urbana. The left one right now is still for sale in this market right now. It's a little tough. I have an appointment with a potential home buyer tonight, though, so I'm hopeful that we finally can get it sold. And this other one was sold in 2006.
Did you have a floor and wall connection to that? Where you were showing the section? All right, that's slightly.
This one?
Yes. How do we connect the floor to the wall?
The wall, the 2x3, or now we went to 2x4. Those walls are lag bolted into the TJI. And then that interior 2x4 wall is being just business as usual connected to the slab. Okay, so this one is a very exciting project for me. Does somebody? I don't have the time. What's the? Oh yeah, excellent, good. Yeah, right. This was the first retrofit that we did and that we consulted on, and it is in Berkeley, California. So I'm really happy about this slide because everybody always thinks like passive houses are super insulated and they only work in cold climates. This one is a passive house in California with a palm tree in front of it. The wall thickness compared to the passive house wall in Urbana is 6 inches in California. In Urbana, it's 16. So we can see how the thickness of the passive house wall varies depending on climate. This one is my house. We built that in started in 2002, 2003. Phenomenal. I haven't turned the heat on yet. When it gets a little bit too cold, I basically put a plate out with 10 tea candles, and I can see the temperature rise. It's amazing, and it's so comfortable. Also, a really nice side effect that one will realize if one lives in a passive house, the inside temperatures, like what I was talking about earlier, the temperature, surface temperature is now so comfortably warm that the temperature setting, I'm comfortable at 65. And there's absolutely no, I don't feel cold. So, this is the front a little earlier and the double story. You can see the thickness of the wall right here. So it's a significant change in appearance, but it is also very, it looks very much like masonry. It looks very stable, very grounded. Again, the Tahan residence. This is the Isabella Lake home in Minnesota, which is the 3rd certified passive house in the United States. 9,000 heating degree days. And they are making passive house standard. So, and as you can see, also not necessarily the most advantageous compact shape, right? So once the designer becomes acquainted with the principles of a passive house and the integrated design becomes kind of like second nature, we can pretty much make any shape work. This is going to be part of the tour of the Passive House conference that we have coming up in Duluth this November. So people will be able to see this house. We have like a bus going to 2 projects. This is a little bit of an experiment there. In Duluth, they have lots of sun, but unfortunately at the wrong time. So when it gets really cold in November, they don't have any sun, but they have a lot before and after. So what they are trying to do here, this is an attempt to seasonally store the sun under the slab of the house. They have a significant solar thermal system, and you can see there's PAX tubing laid in where other people have their basement. They have like a foam-lined cavity. They filled it with sand, they filled it with iron pellets, and have the tubing with the liquid run through that. This is the Skyline House. Phenomenal, beautiful project. I've been in it in Duluth. Also close to Passive House standard, overlooking Lake Superior. You can see right here the double stud wall construction. They didn't go with the TJIs. They used just standard double stud. I think those walls are also about 16 inches thick. And then that one, most of you probably potentially have heard of that. This was the winner of the Solar Decathlon last year, Darmstadt University from Germany. They built a passive house. They put a passive house on the mall. And we're going to do the same next year. The Solar Decathlon team of the U of I decided that they wanted to show that we can do that as well. And we're currently working and this one, I don't know, this is a $5 million, 500 square foot house. Little. Yeah, everybody would say like, yeah, I can do that, right? We're going to do it for 100,000. And we're going to have it modularly prefabricated. So at that moment, when that passive house hits the mall, people can order a passive house economically, feasibly available to everybody. And once you have the shell, once the shell is right, with technology advancing, PV prices coming down, you can always later add a PV system if you cannot afford it right away and become truly carbon neutral. And that is really a great opportunity in terms of the passive house design. So this is the Bio House in Bemidji. Also, in November, they have an open house. If anybody is by accident up in Bemidji, phenomenal project. Again, these are the windows that I showed earlier, the OptiVin windows. And this one is truly a carbon neutral passive house. This is our first project in the East. It's on Martha's Vineyard. It is designed to passive house standard. And there's the windmill. I was just there a couple of weeks ago. My car broke down. I had to stay a couple of days extra. Too bad. Well, I saw the windmill go up. Otherwise, I would have not had the opportunity to see it go up. And once it's there, and it's really amazing. And this house, again, as you can see, we were discussing the compact shape. None of it is the case. When I got brought in on this project, this is the master bedroom. The master bedroom was over here. This is the study. The study was its own building, and everything was connected with a glazed corridor. So I was able to convince them to push it together. But still, not a very good surface to volume ratio, right? And then where's all the glazing? The glazing is in the west. You don't want glazing in the west because you need to shade it. East and west glazing is very hard to shade. So we had to deal with that one. Also, to go back, this is the south. Not really like perfect passive solar orientation, right? And we still made it work. The price was 2 inches of more insulation all the way around the envelope. But you can make it work. And insulation, again, is the cheapest thing on site. Okay, now we have 10 more minutes left. Very quickly, multi-family projects are on the rise as the buildings are still, like my house has 16 inches of walls. The two Fairview houses are 16 inches. People say like, oh yeah, small house, easy, can do. No, the small house is worst case scenario because the surface to volume ratio is not good. You're enclosing very little volume with a lot of surface. So as soon you go to multifamily, what happens in Illinois, if we build townhouses, our walls shrink to 9.5 inches. And at that point, we did the comparison, Passive House upfront cost versus Energy Star upfront cost. Passive House pays off sooner than Energy Star. And then after those 7 years, Passive House saves 80% of the energy. Energy Star saves 30%. So if one really starts to look at the cost curve and the payback, it is an incredible opportunity and feasible today. So this is the Kerr Avenue, Illinois project. The city of Urbana put out a proposal not too long ago for a multi-family, townhouse area. And the goal is Passive House and, if not, carbon neutrality, if budget permits. So we started designing a couple townhouses with PV systems integrated into the roof, playing around with a couple schemes right at the moment, different layouts. But the great thing really is, this is the PHPP, the modeling tool for passive houses, that if I design, I have this tool open right from the beginning, and it tells me immediately how my building is doing in terms of energy performance. So you can input everything, the wall thickness, the R values, the window quality, the air tightness, and then it gives you a summary sheet which tells you if you are making Passive House standard or not. So in this case, we're even below Passive House standard. We are at 10 kilowatt hours per square meter in year, which is very, very, very low. This is not very much heating at all. What the program then also does, it has an output what you need in terms of renewable systems to be carbon neutral. And in this case, you can see right here, total emissions, CO2 equivalent, and then you enter your, let's see, hold on. This is the total CO2 equivalent that the house puts out into the atmosphere. And then we added a renewable system that overproduces and that makes us carbon neutral. So that program tells us exactly what kind of a system we need. And we did the calculations. The additional cost, we're still within like about 10% additional cost. We're trying to get that down with more cost trade-offs, and once we get into the actual design, that 10% will shrink. And after rebate, per unit, $20,000 to become carbon neutral. For that one, that's a big chunk of change for 48 units. But if we can find somebody who's willing to sponsor it and to see it as a visionary project. And Urbana has always said, like, we want this to be a replicable model for the United States. We want a carbon neutral development. So people are willing, people are in support, but now we're missing the money, and the credit market doesn't help either, unfortunately. Very quickly, a couple European build examples. They get very creative over there, starting to use solar thermal as shading elements. Townhouses, most everything is multi-unit. Again, shading elements, solar thermal systems. Retrofits, they start to retrofit all the old 50s buildings, all meeting Passive House standard now. This is a community center. This is a factory, also retrofit. This one right there is a gymnasium with all north glass. And this one is a school. Starts to look like a completely normal building, right? So the architects really started to embrace that concept, and they started to apply it just as if it is a completely standard building. This was, until recently, the largest office building Passive House standard. And this is a single-family home that is using the curtain wall that I showed earlier, the thermally broken Passive House curtain wall system. And this, I'm very happy to show this one. I was having workshops a couple weeks ago at PG&E in San Francisco, and I did challenge PG&E. I said, like, look at this. This is the tallest Passive House tower today It's finished by now, and I don't know why that slide is upside down. Wow. Okay. Anyway, this is a passive house tower, and it's the headquarters of the energy agency in Austria, in Linz. An energy agency built a passive house tower that overproduces, that is carbon neutral. So how does that work? They're using, and upside down, vacuum panels in these walls, curtain wall panels. This is glazing, and then on the side right here, PV cells integrated in the skin.
Could you explain what a vacuum panel is?
Yeah, the vacuum panel is basically, it looks like vacuum coffee, sealed, just that there's silica in it, and the vacuum is being sucked out of that package, and it creates a very high insulative package. Okay, final conclusions. 15 kilowatt hours per square meter near. You have all these metrics on the sheets that I distributed earlier. For cooling, the same. Total primary energy demand, 120 kilowatt hours per square meter a year. That means we're taking into account the losses from the coal-fired plant to the plug. So site energy would be about 40 kilowatt hours per square meter a year. By a factor of 3, we're losing energy. And the air tightness is 0.6. This is California, Europe, Illinois, a couple like R values just to compare. California needs 22 R, Europe needs 38 R, and here in Illinois we need about 56 R for the wall. And this, I love this slide. In 1996, they had 10 passive houses in Germany. It was exactly the same situation like we have right now. Building was down. People were spending very little. Almost all construction businesses went bankrupt, except the tiny little branch of passive housing kept going exponentially. And now they have over 10,000 units, and I think we can repeat this here, turn it around on a dime, put out carbon neutral houses, and put a stop to global warming. I'm going to skip this. Quality approved passive houses, we certify. We are authorized from the Passive House Institute in Darmstadt. We're the official only certifier for passive houses in the United States currently. And you're all cordially invited for the 3rd annual North American Passive House Conference. The whole is greater than the sum of its parts. And we're in Duluth this year, and we have 2 houses on the tour that we will be able to see, including the mechanical systems, the Skyline House that I showed earlier, as well as the Isabella House. Thank you very much.
That was a lot of information. We've got time for a few questions. If anybody does have to leave, they can, but let's entertain a few questions. Yes.
Yeah.
You talked about retrofitting for a moment.
Mm-hmm.
There's a lot of people in the area. I live in a drafty old farmhouse that's 88 years old.
Mm-hmm.
So recently I'm thinking more and more about, insulating, residing, and maybe going with something like geothermal.
Mm-hmm.
But according to Passive House concept, I wouldn't even need the heating, cooling, but what are the costs and trade-offs?
Well, the question was that if you wanted to retrofit your house, he was thinking about retrofitting and using geothermal, but now he's thinking like, with a passive house, you wouldn't even need that big of a system or that expensive of a system. And that's exactly right. Like if you are ready to really significantly invest in your old building and retrofit it really to passive house standard, you can basically eliminate that heating system. But then again, it would basically involve the whole enchilada. The air tightness is very difficult in retrofit. Harold Orr is a champ in retrofitting, and he has coined the term the chainsaw retrofit. He goes ahead and just first cuts all the overhangs off in a building. Then the exterior gets resided, actually resheathed, and that is your airtight layer. And then you also redo the roof at the same time. But, that's costly.
Maybe there's a happy medium somewhere where
Right. Yep.
I insulate to the greater
Yep.
incorporate passive
Mm-hmm.
cooling to a greater extent, where I would only need a much smaller unit.
Exactly.
for screens and-
Yes. And you probably also already have a unit, right? So you might want to consider to stay with your old furnace, but make your envelope way more efficient, so you only need very, very little heat. So that's an option.
In terms of retrofitting, we have a lot of houses around here with 6 to 9 inches of vats
Mm-hmm.
in the attic. Is there something that's recommended for greatly increasing the R value of an existing attic? It's not super thick.
That is not super thick.
You mentioning very efficient
Mm-hmm.
thin material.
Right. The vacuum insulation, that is something that you could apply from the inside. But again, that's pricey, and I don't know if that is really there yet. I mean, unfortunately, we're still kind of like right now stuck with the traditional insulation materials like cellulose, fiberglass, foam.
Another
So-
question then, is there a fabric that you could use as a curtain to wall off part of your house? For example, you had a hallway with 2 or 3 bedrooms down the end that aren't used anymore. Is there something you can put inside of like a curtain across the hallway, possibly over a window that would have a high insulated value?
You could do that. I would recommend against putting like insulative fabrics in front of a window, because most windows most likely are only double pane and uninsulated frames. So what happens if you insulate it from the inside, you're actually making the interior surface colder than as if you had it not insulated. Because now the warm air from the room cannot get to the window anymore. So what happens? You get condensation on that window. Interior insulation is only then helpful with a window if you really also seal the vapor out of that space. Otherwise, you might create more problems than you actually solve. So, I don't know.
I want to get back to some of the bigger picture. What do you think it would take politically to then get us all to adopt passive house as building standards?
It will take what they did in Europe and what they did in the UK. The UK is requiring every building to be emission zero, carbon neutral by 2016. That's what it will take. And very aggressive subsidy programs for retrofitting. And European Union is intending to make passive house standard the code by 2015. Yeah.
So you said it takes about 7 years for the payoff
Mm-hmm.
right now.
For multifamily, yeah.
So how much is the variable house you're selling?
The second one we're selling for 127,000. 1,350 square feet.
And they had carbon neutral and carbon.
Well, it's not carbon neutral yet. It's the shell. But the shell is going to save energy forever, right? So you can upgrade as technologies become cheaper and more available.